Welcome to the second module of the course Linear Algebra for Data Science. The second module deals with the topic vector space. First of all, let us see what a vector space is. A set of objects V equal to set U, V, W, etc. and scalars alpha, beta, gamma, etc. along with a binary operation of vector addition plus on the objects and a scalar multiplication dot is a vector space if it possesses 10 properties. So let us see what the 10 properties are. But before that, remember, in order to consider a vector space, we must have a set of objects V and a set of scalars, and we must have two operations. One of them must be a binary operation, and the binary operation is usually called vector addition. Remember, the vector addition is not the usual plus which we consider. It can be any binary operation, and we have a scalar multiplication. Now, if it is a vector space if it possesses the following 10 properties. So the first 5 properties deals with addition. First property is closure under addition. That is, suppose we have two members U and V in the set capital V, then their sum U plus V must also be a member of capital V. The second property is the commutative law for addition. That is, if U and V are elements of V, then U plus V must be equal to V plus U. The third property is the associative law for addition. That is, suppose we have three elements U, V and W in capital V, then U plus V plus W must be the same as U plus V plus W. The fourth property is there must always exist a zero vector in capital V which is denoted by our 0, such that for every vector U in capital V, U plus 0 must be equal to U. Remember, this 0 is just a symbolic representation of the zero vector in capital V. It need not always be the number 0. The fifth property is for every vector U in capital V, there must exist an additive inverse minus U such that U plus minus U must be equal to the 0 vector. So these are the 5 properties under addition. Now we have 5 properties under scalar multiplication. The first one among them is the closure under scalar multiplication. That is, if U belongs to capital V, then for any scalar alpha, alpha dot U must be an element of capital V. So whatever be the scalar alpha we choose, alpha dot U must be a member of capital V. The second property is for any two scalars alpha and beta and any vector U in capital V, alpha dot beta dot U must be the same as alpha beta dot U. That is, suppose we take the product of beta with U first, and then the results product, if we are taking the results product with alpha, it must be the same as alpha beta times U. The third property is for any vector U in capital V, the scalar 1 times U must always be equal to U itself. S4 is for any two scalars alpha and beta and any vector U in capital V, alpha plus beta times U must be equal to alpha dot U plus beta dot U. That is a distributive property. And the fifth and the final property is that for any scalar alpha and any two vectors U and V in capital V, alpha dot U plus V must be the same as alpha dot U plus alpha dot V, which is the next distributive property. So if these 10 conditions are satisfied, we say that capital V is a vector space. If any of these conditions are being violated by the set capital V, we say that capital V is not a vector space. A very familiar vector space we know is the real numbers. The set of all real numbers actually forms a vector space. Then the 0 vector is the number 0. And for any two real numbers, their sum is again a real number. The product of any real number with any scalar is again a real number. So we say that the set of all real numbers under the set of all scalars, that is the set of all scalars must also be the set of real numbers. Then only this property will be satisfied. Then R is a vector space. Okay, so this the real number system is a vector space, and the set of all scalars which we consider is very important, because as a set of scalars vary, the given vector capital V might be a vector space or not. For example, suppose we consider capital V as the set of all real numbers and the set of all scalars as the set of all complex numbers. Then consider the complex number I. I dot any real number, say 2, is actually 2i, and it is not a real number. So it does not satisfy S1. Okay, so this is the set of all real numbers is not a vector space when the set of scalars we consider are complex numbers. So the set of scalars we consider are also very important. And if the set of scalars we consider are complex numbers, we call the vector space a complex vector space. And if the set of scalars we consider are real numbers, the vector space is called a real vector space. Let us see the first example. Prove that R2 means the set of all vector elements of the form AB matrices 1 by 2 matrices AB such that A and B are real numbers. Prove that this is a vector space under regular addition and scalar multiplication. So the set of all elements which we consider here are of the form set AB, where A and B are real numbers. And what is a binary operation which we consider here? It is a regular addition of matrices. And the regular scalar multiplication is the second operation which we consider here. Okay. Now let us try to prove it. So in order to prove that R2 is a vector space, we have to prove all the 10 properties. So let U, V and W be arbitrary elements in R2. Now the first property is closure under addition. So U plus V. What is U plus V? That is U plus V is equal to AB plus CD. That is the same as under regular matrix addition, this will be equal to A plus C, B plus D. Again, this is an element of R2. So U plus V belongs to R2, or in other words, A1 is being satisfied. Now let us consider A2. A2 is commutative law for addition. So U plus V is A plus C, B plus D, and we know A, C, B and D are real numbers. So real numbers satisfy the commutative law of addition. So A plus C is the same as C plus A. That is 1 plus 2 is the same as 2 plus 1. For any real numbers, this property is being satisfied. So A plus C is the same as C plus A, and B plus D is the same as D plus C. That is U plus V is the same as V plus U. What is A3? U plus V plus W. That is AB plus C plus E, D plus F. That is the same as A plus C plus E, B plus D plus F. Now you can write it as the same as A plus C plus E plus, B plus D plus F. That is U plus V plus W. So U plus V plus W is the same as U plus V plus W. That is, associative law for addition is also being satisfied. Now what is A4? There must exist a zero vector 0 such that for any vector U in R2, U plus 0 must be equal to U. So this zero vector, remember the zero vector must be an element of R2 itself. So what is a zero vector we can consider there? It is 0, 0, right? 0, 0 is an element of R2, and for any vector AB belongs to R2, AB plus 0, 0 is equal to AB itself. So this is the zero vector which we consider here. So 0, 0 belongs to R2 such that U plus 0 is equal to U. Now what is A5? for any vector u belongs to R2, there must exist a minus u belongs to R2. So let us consider u as AB. Then what is minus u? Minus u can be considered as minus A minus B. What should minus u satisfy? Minus u must satisfy u plus minus u is equal to, here what is it? AB plus minus A minus B is equal to A minus A, B minus B, this is equal to 0, 0. So for any vector u in R2, there exists a minus u in R2 such that u plus minus u is equal to 0, 0. So all the 5 properties of vector addition are being satisfied here. Now let us consider all the 5 properties of scalar multiplication. So for any two real numbers alpha and beta, first property is alpha dot u must be an element of R2. So alpha is any scalar. Here we consider the scalars as real numbers. Okay. So scalars are real numbers, remember. So for any scalar alpha, say alpha is equal to 2 for example, 2 times AB is 2A, 2B, right? Which is again an element of R2. So for any scalar alpha in general, alpha dot u is alpha A, alpha B, which is an element of R2. So the closure under scalar multiplication is being satisfied. What is the second property? Alpha dot beta dot u is equal to, alpha dot beta dot u is equal to alpha dot beta A beta B, that is equal to alpha beta A alpha beta B. So alpha beta is a common factor which can be taken outside. So this can be written as alpha beta times AB, that is alpha beta dot AB, that is equal to alpha beta dot u. So S2 is being satisfied. What is S3? S3 is 1 dot u. 1 is the real number 1 here. We consider the real number 1. So 1 dot u is 1 dot AB, which is AB itself. So 1 dot u is the same as u. What is S4? S4 is a distributive property. Alpha plus beta times u is, that is equal to alpha plus beta dot AB, that is equal to alpha plus beta, we just give it to both the elements, alpha plus beta times B, which is equal to, now you can open this bracket, right? So that is alpha A plus beta A, alpha A plus beta A, and alpha B plus beta B, which is equal to alpha A alpha B plus beta A beta B, and that is equal to alpha times AB plus beta times AB, that is equal to alpha dot u plus beta dot u. So this property is also being satisfied, and the final property is alpha dot u plus v is equal to, alpha dot u plus v is equal to alpha dot AB plus CD, which is equal to alpha dot A plus C, B plus D, that is equal to alpha times A plus C and alpha times B plus D, that is equal to alpha A plus alpha C alpha B plus alpha D, that is equal to alpha A alpha B plus alpha C alpha D, and that is equal to alpha dot AB plus alpha dot CD, that is equal to alpha dot U plus alpha dot B. Therefore, R2 satisfies all the properties of a vector space. So R2 is a vector space under regular matrix addition and scalar multiplication, where the set of all scalars we consider are real numbers. Suppose we consider the set of all complex numbers as the scalars, then R2 will not be a vector space because the closure under scalar multiplication will not be satisfied. That is, suppose we consider alpha as I, then alpha dot u is equal to I times AB, that is equal to IA IB, which is actually not an element of R2 because IA and IB are not real numbers. R2 consists of all matrices of the form AB, where A and B are real numbers. So, if the scalars we consider are complex numbers, R2 is not a vector space. So, it is important to specify the set of all scalars. So, in general, we have now proved that R2 is a vector space. R2 is a set of all elements of the form A, B. Now, Rn, this can also be written as column matrices. Okay, so this can be written as column matrices also. That is also the same. Okay, so in general, Rn is the set of all elements of the form, set of all n tuples A1, A2, etc. An, where A1, A2, etc. An are real numbers. This Rn is a vector space under usual addition and scalar multiplication. Remember, the set of scalars we consider, if not mentioned, the set of all scalars we consider are always real numbers. Okay, if the set of scalars are mentioned to us, you have to consider them. If it is not mentioned, it means that the scalars are always real numbers. Okay, so Rn is always a vector space. That is, in particular, R3 is of the form set of all A, B, C. This can also be written as set of all A, B, C. Row matrix or a column matrix, both are the same. Okay, so R3 is a vector space, R4 is a vector space, or in general, Rn is a vector space. So this is the first and the important example of a vector space. Let us see another example. Show that M2 by 2 is a vector space. What is M2 by 2? M2 by 2 is a set of all 2 by 2 real matrices. And prove that, we are asked to prove that it is a vector space under standard matrix addition and scalar multiplication. So, we'll prove all the 10 properties one by one as we have done in the case of R2. Here again we consider three matrices A, B and C. Let them be arbitrary elements of M2 by 2. What is the first property? A plus B. A plus B is the sum of two 2 by 2 matrices. It is again a 2 by 2 matrix, we know. So, sum of two, since the sum of two 2 by 2 matrices is again a 2 by 2 matrix, the closure under addition is being satisfied. And matrix addition is always commutative. So, A plus B will always be B plus A. So, the commutative property of addition is being satisfied. And matrix addition is also associative. We know all these properties. So A plus B plus C will be the same as A plus B plus C. What is the fourth property? We know there must exist a zero vector. What is a zero vector here? It is a zero matrix itself. It is a 2 by 2 zero matrix such that A plus 0 is equal to A itself. Now for any A belongs to M2 by 2, what is the additive inverse of A? It is the matrix minus A. So for A is equal to A, B, C, D belongs to M2 by 2, there exists minus A which contains all the negatives of elements of M2 by 2 such that A plus minus A is equal to the zero matrix. So all the 5 properties of vector addition are being satisfied here. Now let us consider all the 5 properties of scalar multiplication. Now, if we multiply a real number to a 2 by 2 matrix, we know we again get a 2 by 2 matrix where each element of the matrix are being multiplied by the number. So, closure under scalar multiplication is satisfied. What is the second property? Alpha dot beta dot A. It is the same as alpha beta A, alpha beta B, alpha beta C, alpha beta D. So, alpha beta is a common factor which can be taken outside and can be written as alpha beta times AB. So, even if we take the product of beta with A first and then take the results product with alpha, it is the same as taking the product of alpha beta with A. So, S2 is satisfied. Now, if we multiply 1 with a matrix A, we get the matrix A itself. So S3 is also satisfied. Similarly, we can prove S4 and S5. It can easily be proved that both the distributive properties can easily be proved. So therefore, M2 by 2 is a vector space under regular matrix addition and scalar multiplication. Here also, since the set of scalars are not specified to us, we consider them as real numbers. So M2 by 2 is a vector space. In general, we can easily prove that MP by N is actually the set of all P by N matrices. This is a vector space under regular matrix addition and scalar multiplication. That is, in particular, M2 by 3 is a vector space, M5 by 4 is a vector space, M3 by 7 is a vector space. In general, MP by N is a vector space. What is M3 by 7? M3 by 7 is a set of all 3 by 7 real matrices. Okay, so that is what here it is said. In general, the set MP by N of all P by N real matrices under matrix addition and scalar multiplication is a vector space. Now let us see the next question. Determine whether the set of all 2 by 2 real matrices is a vector space under regular scalar multiplication but with vector addition defined to be matrix multiplication. That is, U plus V is equal to UV. That is, remember I have told you in the beginning, the vector addition which we denote using this plus symbol is not always the regular addition which we consider. Regular addition we consider as 2 plus 3 is equal to 5. But this actually is only a symbolical representation of vector addition. Any binary operation can be considered as vector addition. So here the vector addition we consider is the matrix multiplication. So U plus V is not adding two matrices, but here it is considered as U into V. So if you have any confusions, you can write it using this symbol. So this actually does not denote regular addition, but it can be any binary operation. Here we consider the binary operation as matrix multiplication. So the question is whether it is a vector space. So the set we consider here is a set of all 2 by 2 real matrices. Scalar multiplication is just the same, but vector addition differs. Then will it form a vector space? What do you think? Let us consider a particular example. Here, consider two 2 by 2 matrices 1, 2, 3, 4 and 5, 6, 7, 8. So we are adding these matrices. Remember, this vector addition is not the regular addition. It is matrix multiplication here. So on multiplying these matrices, you get the matrix 19, 22, 43, 50. So this is U plus V. Okay. It is a 2 by 2 matrix. So closure under addition is satisfied. Closure under vector addition is satisfied because product of any two 2 by 2 matrices is again a 2 by 2 matrix. Okay. But is U plus V equal to V plus U here? We know matrix multiplication need not always be commutative. So here U plus V is 19, 22, 43, 50. But what is V plus U? It is 23, 34, 31, 46. So these two matrices are not equal. That is, U plus V is not equal to V plus U. So this set of matrices under this vector addition do not satisfy the commutative law for addition. So we can say that the given set of 2 by 2 matrices under the given vector addition and scalar multiplication is not a vector space. But we have already seen in the previous example the set of all 2 by 2 matrices under regular matrix addition and scalar multiplication forms a vector space. This means that the set of vectors we consider, the set of scalars we consider, the vector addition we consider and the scalar multiplication we consider are all equally important in determining whether the given set is a vector space. Okay, so sometimes the sets may be fine, the scalar multiplication may be fine, but here the vector addition we defined was not enough for us to prove, to show that the given set is a vector space. Okay, so in order to prove that a given set is a vector space, you will have to prove all the 10 properties, but for disproving we only have to show a counter example. So here itself we can say that the given set is not a vector space. Now there are two questions for you to try, for the reader to work out. The first question is, prove that R3 is a vector space under usual addition and scalar multiplication. We have already proved that R2 is a vector space. So this is R3. What is R3? R3 is the set of all matrices of the form A, B, C, where A, B and C are real numbers. Okay, so prove that this is a vector space under regular matrix addition and scalar multiplication, and since the set of scalars is not specified to you, you can consider them as the set of real numbers. The fourth one is the second question is, determine whether set of all 2 by 2 matrices. Here there is a peculiarity for this 2 by 2 matrices. There is a restriction given. This entry must always be 1. Prove that this is a, you are not asked to prove it, you are asked to determine whether the given set is a vector space. That is, here an element will always be of the form A, B, 1, D. Okay. Another element will be of the form E, F, 1, H. So you are asked to prove or disprove that the given set is a vector space. Okay. So these two problems you can try to work out by yourself. Thank you.